July 18th, 1985, 1147 hours. Moscow. Colonel Leonid Sergeyevich Zaitsev sat at his desk in the KGB headquarters at Lubyanka Square, reading through the final draft of a report that had consumed 6 months of his professional life, and would, he suspected, destroy what remained of Soviet confidence in their ability to compete with the West in advanced technology. The report was 247 pages long, classified top secret with the additional designation special importance, and it documented in meticulous detail exactly how far behind the Soviet semiconductor industry had fallen compared to American capabilities. But more than that, it explained why the gap could never be closed using Soviet methods, why every attempt to steal or copy Western technology only demonstrated more clearly the fundamental inadequacy of the Soviet industrial system. Zaitsev was Deputy Chief of Directorate T, the KGB's Scientific and Technical Intelligence Directorate, responsible for acquiring Western technology through espionage, legal purchases, and analysis of openly available technical information. He had worked in technical intelligence for 19 years, managing operations that stole computer designs, semiconductor manufacturing equipment, telecommunication systems, everything the Soviet Union needed but could not produce domestically. It was demanding work that required both technical expertise and operational skill, coordinating networks of agents across Western Europe and North America, analyzing stolen materials to determine their military and economic value, reporting to Soviet leadership on Western technological capabilities. For most of his career, Zaitsev had believed the work was succeeding. Soviet intelligence acquired enormous quantities of Western technology. The shopping lists that came from Soviet industrial ministries and military design bureaus were comprehensive, and Directorate T filled most of them. Thousands of technical documents stolen or purchased, hundreds of pieces of equipment smuggled through complex networks that evaded COCOM export controls. Entire production lines acquired through front companies and shipped to the Soviet Union. The scale of technology acquisition was unprecedented, the largest peacetime industrial espionage program in history. But Zaitsev had gradually come to understand that acquisition was not the same as capability. Soviet factories received stolen equipment and could not operate it properly because they lacked the trained personnel, the supporting infrastructure, the quality control procedures that made the equipment work in Western facilities. Soviet engineers received stolen technical documents and could not replicate the designs because they lacked access to the materials, the precision manufacturing tools, the testing equipment that Western engineers took for granted. The Soviet Union was stealing technology at an enormous rate and falling further behind despite those thefts. The report on his desk documented this failure comprehensively. It had been commissioned in December 1984 by the Central Committee's Commission on Military Industrial Questions, chaired by Nikolai Ryzhkov, who was then a Central Committee secretary before becoming premier. The commission wanted to understand why Soviet microelectronics continued to lag Western capabilities despite massive investment in technology acquisition and reverse engineering. They wanted actionable intelligence that could guide policy decisions about how to respond to the growing technology gap. What they got instead was a report that proved the gap was unbridgeable, that the Soviet system was fundamentally incapable of competing with Western semiconductor industry, that every ruble spent on technology theft was essentially wasted because the underlying problem was not access to technology, but the structure of the Soviet economy itself. Zaitsev had assembled a team of 12 technical intelligence officers and 7 outside experts from Soviet research institutes to compile the assessment. They had analyzed thousands of pages of intelligence on American semiconductor companies. They had interviewed defectors with knowledge of Western manufacturing practices. They had examined every major technology acquisition operation from the previous 5 years, determining which had succeeded in enabling Soviet production capabilities and which had failed. And they had consulted with engineers from Zelenograd's research institutes, the men who actually tried to implement stolen technology in Soviet facilities. The findings were devastating and unambiguous. American semiconductor industry was not simply ahead of Soviet capabilities in degree, but was operating according to fundamentally different principles that made direct comparison almost meaningless. It was like comparing a modern factory to a medieval workshop. Both might produce similar products, but the methods, the efficiency, the quality were so different that they existed in separate technological epochs. The report's first section documented the current state of American semiconductor technology as of mid-1985. Intel had introduced the 80286 microprocessor in 1982, containing 134,000 transistors manufactured using 1.5 micrometer process technology. They were already developing the 80386, which would contain 275,000 transistors using 1.0 micrometer processes. Motorola was producing the 68020 microprocessor with 190,000 transistors. These chips operated at speeds exceeding 10 megahertz, executed millions of instructions per second, and were manufactured in facilities achieving production yields of 70–80%. Soviet industry in 1985 was producing chips equivalent to Western designs from the mid-1970s. The most advanced Soviet microprocessor in volume production was the KR1810VM86, a clone of Intel's 8086 processor from 1978. The Soviet version contained approximately 29,000 transistors, manufactured using 3.0 micrometer processes in facilities that achieved yields of 20–30%. The chips operated at 5 MHz maximum, half the speed of the original Intel design, and even then, many units failed to meet timing specifications. Soviet engineers joked bitterly that they had finally achieved parity with American technology from 7 years ago, except they had achieved it poorly. The report included detailed technical comparisons across multiple dimensions: manufacturing process technology, materials purity, equipment capabilities, design tools, testing procedures, quality control methods. In every category, Soviet capabilities lagged American standards by 5 to 10 years. But the most damning comparisons were not technical specifications, but economic metrics that revealed the true scale of Soviet industrial inadequacy. American semiconductor companies in 1985 were investing approximately 15–20% of revenues in research and development, constantly pushing the frontier of what was technically possible. Intel spent over $300 million annually on R&D, more than the entire budget of all Soviet semiconductor research institutes combined. This investment was driven by competitive pressure. Companies that failed to innovate lost market share to competitors and eventually went bankrupt. The industry was ruthlessly efficient at allocating capital to the most promising technologies and most capable companies. Soviet semiconductor research received funding through the state budget, allocated according to 5-year plans that were determined by political negotiations rather than technical merit. Research institutes had guaranteed funding regardless of whether their work produced useful results. There was no mechanism to shut down unproductive programs or to redirect resources to more promising approaches. Innovation happened slowly when it happened at all, driven by individual researchers' dedication rather than systematic pressure to improve. The report's second section examined Soviet technology acquisition efforts, documenting both successes and failures. This section was particularly sensitive because it included information on intelligence operations that were ongoing, but Zaitsev had argued that honest assessment required acknowledging what actually worked rather than what propaganda claimed worked. Directorate T operated through Line X officers stationed in Soviet embassies and trade offices throughout the West. These officers recruited sources with access to Western technology, established front companies that could legally purchase equipment subject to export controls, and coordinated with GRU military intelligence and scientific attachés to provide comprehensive coverage of Western technological developments. The operation was massive in scope. At any given time, Line X was managing several thousand active sources and monitoring thousands of Western companies for acquisition opportunities. The shopping list for semiconductor technology alone ran to hundreds of pages. Photolithography equipment capable of sub-2 micrometer resolution. Ion implantation systems for precise doping control. chemical vapor deposition reactors for growing thin films, testing equipment that could characterize chip performance at high speeds, design automation software that could handle complex circuits with hundreds of thousands of transistors, ultra-pure silicon wafers, specialty chemicals, and gases. The list was comprehensive because Soviet industry could produce almost none of these items domestically at quality levels required for modern semiconductor manufacturing. Line X had succeeded in acquiring much of this equipment and material. The report documented dozens of successful technology transfer operations from the early 1980s. A photolithography stepper from Perkin-Elmer, purchased through a Swiss front company and smuggled to the Soviet Union via Vienna. Ion implantation equipment from Varian Associates, acquired through an intermediary in Singapore. Chemical vapor deposition reactors from Applied Materials, stolen when a disgruntled employee sold technical specifications and operating manuals. The acquisitions represented years of patient intelligence work and cost the Soviet Union hundreds of millions of dollars in payments to sources, equipment purchases, and smuggling operations. But the report's analysis revealed that these successful acquisitions had produced minimal improvement in Soviet semiconductor capabilities. The Perkin-Elmer stepper had been installed at a facility in Zelenograd with great fanfare in 1983. It should have enabled Soviet production of chips using 1.5 micrometer process technology, matching American capabilities from the early 1980s. In reality, the stepper achieved inconsistent results because Soviet cleanrooms could not maintain the contamination control standards required for reliable operation. Dust particles that would have been filtered out in Western facilities landed on wafers during processing, creating defects that destroyed chips. The stepper's optical system required calibration using specialized test equipment that Soviet facilities lacked. When something broke, which happened frequently, replacement parts had to be smuggled from the West because Soviet manufacturers could not produce equivalents. After 2 years of operation, the facility using the Perkin-Elmer stepper was achieving yields of approximately 25% for circuits that should have yielded 70% in Western facilities using the same equipment. The stolen equipment was working as designed. The problem was that everything around the equipment, the cleanroom environment, the wafer quality, the chemicals, the trained personnel, the maintenance procedures, was inadequate by Western standards. The Varian ion implanter had similar problems. It was sophisticated equipment requiring precise calibration and regular maintenance. Soviet technicians had been trained to operate it, but their training consisted of memorizing procedures without understanding the underlying physics. When operational parameters needed adjustment for different processes, the technicians had no basis for making those adjustments intelligently. They followed recipes exactly, and when recipes needed modification for Soviet conditions, the modifications were done through trial and error that wasted time and materials. Zaitsev had interviewed the chief engineer at the facility where the Varian implanter was installed. The engineer had been candid in ways that few Soviet technical specialists allowed themselves to be. "Comrade Colonel, we have world-class equipment sitting in a third-rate factory. The implanter works perfectly, but it feeds into processes that introduce defects, that create contamination, that operate outside normal specifications because our equipment is inadequate. It is like installing a precision engine in a tractor. The engine works, but the entire vehicle is still a tractor." The report included a particularly devastating section on reverse engineering efforts. Soviet engineers had successfully reverse engineered numerous American chips, documenting their circuit designs and manufacturing processes with impressive technical skill. But translating those reverse engineered designs into working Soviet products proved extraordinarily difficult. The KR-1810 VM86, the Soviet 8086 clone, had required 4 years of development from the time Soviet engineers first examined the Intel original to the time the Soviet version entered production. The original Intel 8086 used 3.0 micrometer process technology that should have been accessible to Soviet manufacturing capabilities. But Soviet engineers discovered that matching the design exactly was impossible because Soviet materials and equipment could not replicate the precise characteristics of the American version. Intel's 8086 used a specific type of silicon substrate with carefully controlled electrical properties. Soviet silicon wafers had higher impurity levels that changed the transistor characteristics, requiring circuit redesign to compensate. Intel's metallization used aluminum alloy with precise composition that provided reliable electrical connections. Soviet aluminum was less pure, more prone to electromigration failures, requiring thicker metallization that increased resistance and reduced performance. Intel's photoresist materials could reproduce fine features with high fidelity. Soviet photoresist was less sensitive, less capable of resolving small features, forcing Soviet designers to modify circuit layouts to use larger feature sizes. Every difference between Soviet materials and American equivalents required design modifications. The accumulation of these modifications meant that the KR1810VM86 was not truly compatible with the original 8086 despite being called a clone. It operated more slowly, consumed more power, generated more heat, and failed to meet timing specifications that the original Intel chip exceeded comfortably. And it took 4 years of intensive engineering effort by some of the most talented engineers in the Soviet Union to achieve these mediocre results. The report calculated that Soviet industry had invested approximately 50 million rubles in developing the KR1810VM86, equivalent to roughly $80 million at official exchange rates, or perhaps $300 million in real purchasing power given the inefficiencies of the Soviet economy. Intel had developed the original 8086 for approximately $25 million. Soviet engineers spent more than 10 times as much to produce an inferior copy of a chip that was already obsolete by Western standards. And this pattern repeated across the entire Soviet semiconductor industry. Enormous investment in reverse engineering and technology acquisition produced chips that were years behind Western equivalents and inferior in performance. The gap was not closing. If anything, it was widening because Western companies innovated faster than Soviet industry could copy their innovations. The report's third section analyzed why this situation existed and whether it could be remedied. This section was the most politically sensitive because it identified systemic problems with the Soviet economic system that could not be fixed through incremental improvements or increased investment. The fundamental problem was that modern semiconductor manufacturing required an industrial ecosystem that did not exist in the Soviet Union. In the West, semiconductor companies operated within a complex network of specialized suppliers. Equipment manufacturers like Applied Materials and Lam Research built the tools that chip companies used. Chemical suppliers like Dow Corning provided ultra-pure materials. Design automation companies like Mentor Graphics and Cadence developed software tools. Universities trained engineers with specialized knowledge. This ecosystem evolved through market competition, with each company innovating to serve customer needs better than competitors. The Soviet Union had attempted to create a similar ecosystem through central planning. State committees directed research institutes to develop equipment and materials for semiconductor manufacturing. Universities trained engineers according to standardized curricula determined by education ministry officials. Everything was coordinated through plans that specified production targets, resource allocations, and development schedules. But planning could not replicate the evolutionary dynamics of market competition. Western equipment companies invested heavily in R&D because customers demanded better performance and would buy from competitors if performance did not improve. Soviet equipment manufacturers received funding regardless of whether their customers were satisfied. There was no competitive pressure driving improvement, no mechanism to shut down unproductive programs, no way to redirect resources from failing approaches to promising alternatives. Western chemical suppliers maintained rigorous quality control because customers would reject batches that did not meet specifications and purchase from other suppliers. Soviet chemical plants had guaranteed customers who had no alternatives. Quality varied wildly between batches because maintaining consistent quality required investment in equipment and training that did not improve the plant's ability to meet production quotas, which were measured in tons of output rather than purity levels. Western design automation companies raced to develop better software tools because chip designers would pay premium prices for tools that saved time and enabled more complex designs. Soviet research institutes developed software according to 5-year plans that specified general goals but provided no feedback from actual users. The resulting tools were crude, difficult to use, and often incompatible with the equipment Soviet engineers actually had access to. Every component of the ecosystem suffered from similar problems. The cumulative effect was that Soviet semiconductor manufacturing operated with equipment that was obsolete, materials that were impure, software that was inadequate, and trained personnel who lacked the specialized knowledge that Western engineers acquired through experience and continuous learning. Zaitsev had included in the report a case study that illustrated these systematic failures with particular clarity. In 1982, Line X had acquired a complete set of design files for the Motorola 68000 microprocessor, one of the most advanced chips available at that time. The files included complete circuit schematics, mask layouts, manufacturing process specifications, testing procedures, everything necessary to manufacture the chip. It was an intelligence coup that should have allowed Soviet industry to produce a 68,000 clone within a year or two. 3 years later, Soviet engineers had still not produced a working 68,000 clone. The design files were complete and accurate. The problem was that Soviet manufacturing capabilities could not execute the design as specified. The 68,000 used 3.5 micrometer process technology, which should have been accessible to Soviet facilities. But the chip's design made assumptions about manufacturing precision and consistency that Soviet facilities could not meet. The 68,000's complex instruction decoder required transistors with very precise characteristics. Small variations in transistor threshold voltage, which were normal in Soviet manufacturing, caused the decoder to malfunction. Soviet engineers attempted to redesign the decoder to tolerate larger variations, but this required understanding the design intent at a level that the stolen files did not provide. They made changes through trial and error, testing different approaches, gradually modifying the design until it worked with Soviet manufacturing processes. After 3 years, they had produced a modified version that functioned at about half the speed of the original Motorola chip and failed quality testing approximately 60% of the time. The project was ongoing, consuming the efforts of hundreds of engineers, and it remained uncertain whether it would ever produce a chip that met military specifications for use in Soviet weapon systems. "We are trying to run before we can walk," one engineer told Zaitsev during an interview for the report. The Americans developed their technology incrementally, each generation building on lessons from the previous one. They make small improvements continuously, refining their processes, learning from failures. We try to skip 5 years of development by stealing their designs, and we discover that we do not have the foundational capabilities to implement what we stole. So we go back and try to develop those capabilities, but by the time we succeed, the Americans have advanced another 5 years. We are trapped in a cycle where copying keeps us perpetually behind. The report's fourth section addressed the question that Zaitsev knew Soviet leadership most wanted answered. Could the gap be closed? Could Soviet microelectronics achieve parity with the West? The honest answer was no, at least not using current Soviet methods and within any time frame that mattered strategically. The report documented this conclusion through detailed analysis of what would be required to match American semiconductor capabilities. To achieve parity, Soviet industry would need to develop or acquire manufacturing equipment equivalent to Western capabilities. This meant photolithography tools with sub-1 micrometer resolution, which Soviet optics industry could not produce. It meant advanced etching systems using plasma-based processes that Soviet equipment manufacturers had attempted unsuccessfully for years. It meant deposition equipment capable of growing films with atomic layer precision. The equipment gap alone represented perhaps a decade of development, assuming Soviet engineers could solve all the technical problems, which was far from certain. Even with equivalent equipment, Soviet facilities would need to achieve contamination control comparable to Western cleanrooms. This required not just air filtration systems, but entire facilities designed around contamination control principles. The buildings needed proper seals to prevent outside air infiltration. The construction materials needed to be non-particle generating. The HVAC systems needed redundancy to ensure constant operation. Soviet construction industry worked to very different standards. Retrofitting existing facilities was nearly impossible. Building new facilities would cost hundreds of millions of rubles per facility, and the Soviet Union would need dozens of such facilities to supply military and civilian requirements. Materials quality would need dramatic improvement. Silicon wafer manufacturing would need to achieve purity levels measured in parts per billion. Chemical suppliers would need to produce specialty materials with consistent composition. Gas suppliers would need ultra-high purity products. Each of these requirements demanded capabilities that Soviet chemical industry did not possess and had no clear path to developing. Beyond physical capabilities, Soviet industry would need cultural transformation. Engineers and technicians would need to embrace quality as a primary objective rather than something that was sacrificed to meet production quotas. Management would need to focus on long-term capability development rather than short-term plan fulfillment. Workers would need training in sophisticated procedures and motivation to follow those procedures consistently. These cultural changes would require abandoning fundamental principles of Soviet industrial organization, principles that were embedded in the economic system and protected by Communist Party ideology. The report estimated that achieving parity with American semiconductor capabilities as they existed in 1985 would require 15-20 years of sustained effort and investment of perhaps 50 billion rubles, an enormous sum that represented more than 5% of Soviet GDP annually. And even if this investment was made and all technical challenges were solved, by the time Soviet industry achieved 1985 American capabilities, American industry would have advanced another 15 years, maintaining the gap indefinitely. The conclusion was inescapable. Soviet semiconductor industry could not catch up through technology theft and reverse engineering. It could not catch up through massive investment in domestic development. The gap would continue to widen as long as the fundamental structure of the Soviet economy prevented the kind of continuous innovation and quality improvement that Western industry achieved through market competition. Zaitsev read through this conclusion one final time, knowing that it was accurate and professionally necessary, but also knowing that it would be devastating to Soviet leadership. For 40 years, the Soviet Union had competed with the United States across every dimension of technological and military power. They had achieved nuclear weapons, long-range missiles, space satellites. They had convinced themselves and much of the world that socialist planning could match or exceed capitalist innovation. And now, a 247-page intelligence report was documenting comprehensively that they had lost the competition in what was perhaps the most important technology of the late 20th century. He signed the report, added the required security markings, and placed it in a courier pouch for delivery to the Central Committee. Within a week, it would be read by the most senior officials in Soviet leadership. And then he would wait to see how they responded to truths that were politically intolerable but strategically essential. The report was delivered to the Central Committee on July 22, 1985. Mikhail Gorbachev had become General Secretary just 4 months earlier, and he was already pushing for reforms that would modernize the Soviet economy. The report arrived at a moment when Soviet leadership was particularly receptive to honest assessment of their technological position relative to the West. Gorbachev read the report personally, along with several Politburo members and senior officials from the defense industrial complex. The response was not what Zaitsev had expected. There was no reprimand for defeatism, no criticism of his methodology or conclusions. Instead, there was weary acknowledgement that the assessment was accurate and that fundamental changes would be necessary. In a Politburo meeting in early August, Gorbachev referenced the report directly. "Comrades, we have received comprehensive intelligence on American semiconductor capabilities. The assessment is that we are falling further behind despite massive investment in technology acquisition. Our engineers tell us that the problem is not access to Western technology, but our inability to implement that technology using Soviet industrial methods. This is not a problem we can solve through traditional approaches. It requires rethinking how we organize our economy. It was a remarkable admission. The General Secretary of the Communist Party was acknowledging, based on KGB intelligence, that Soviet economic organization was fundamentally inadequate for competing in advanced technology sectors. The statement would have been impossible under Brezhnev or Andropov, who insisted on maintaining the fiction that Soviet methods were superior to capitalist approaches. But Gorbachev was different, willing to confront uncomfortable realities if that was necessary for reforms. But acknowledging problems and solving them were different things. Over the following years, Gorbachev would attempt economic reforms that were supposed to introduce market mechanisms while maintaining socialist ownership. Perestroika and glasnost would encourage innovation and quality improvement through transparency and accountability. But these reforms came too late and did not go far enough to fundamentally restructure the Soviet economy. Soviet semiconductor industry continued its decline. By 1990, the gap with Western capabilities had widened to perhaps 15 years. American companies were manufacturing chips with millions of transistors using sub-1 micrometer processes. Soviet factories were still struggling with chips from the early 1980s. And the collapse of the Soviet Union in 1991 essentially ended any pretense of catching up. Zaitsev retired from the KGB in 1989, 2 years before the Soviet collapse. In a 1998 interview with a Russian technology journal, he reflected on the 1985 report and its impact. I believed at the time that if Soviet leadership understood how far behind we had fallen, they would take drastic action to fix the problems. I documented everything with precision and honesty, thinking that accurate intelligence would drive rational policy responses. But I underestimated how difficult it is for a system to reform itself when reform requires admitting that the system's fundamental premises are wrong. Did you consider the report a failure? The interviewer asked. No. The report accomplished what intelligence is supposed to accomplish. It provided accurate assessment of threats and capabilities, helping leadership understand their strategic position. But intelligence cannot force good decisions. It can only inform decisions. Soviet leadership read my report, understood its implications, and proved unable to respond effectively because responding would require abandoning the economic principles that justified Communist Party rule. They were trapped by their own ideology. What would you have done differently? Zaitsev was silent for a long moment. I would have written it earlier. By 1985, the technology gap was already so large that closing it was practically impossible. If similar assessments had been written in 1975 or even 1980, when the gap was smaller and the Soviet economy was stronger, perhaps reforms could have succeeded. But we spent years pretending the problem did not exist, filing optimistic reports that claimed Soviet technology was advancing, ignoring evidence that contradicted what leadership wanted to hear. By the time we finally acknowledged the truth, it was too late to matter. The report itself remained classified for decades after the Soviet collapse. When it was finally declassified in 2003, historians recognized it as one of the most important intelligence assessments of the Cold War's final phase. It documented with precision the technological and economic weaknesses that would contribute to Soviet collapse. And it demonstrated that Soviet leadership had access to accurate information about those weaknesses years before the system failed. The report's impact on Soviet morale was significant but difficult to quantify. For engineers and scientists who had dedicated their careers to Soviet technology development, the report confirmed what they had privately known but could not officially acknowledge. Their work was failing. The system they served was inadequate. The competition with the West was already lost in the sectors that would define the future. This realization was psychologically devastating destroying motivation and encouraging the best talent to consider defection or to simply stop trying. For Soviet leadership, the report was a crucial data point contributing to the reform impulses that Gorbachev would pursue. It provided authoritative evidence that the Soviet economy needed fundamental restructuring, that incremental improvements were insufficient, that maintaining the status quo would guarantee steady decline relative to Western capabilities. The report did not cause perestroika, but it contributed to the understanding that change was necessary. And for Western intelligence services that eventually obtained copies through various channels, the report confirmed their own assessments of Soviet technological weakness. It demonstrated that Soviet leaders knew they were falling behind, that they understood the scale of the problem, and that they lacked effective responses. This knowledge influenced Western strategy during the final years of the Cold War, encouraging technology-focused competition that exploited Soviet weaknesses. The KGB Technical Intelligence Report of 1985 broke Soviet morale not through any exaggeration or defeatism, but through comprehensive documentation of realities that Soviet leadership had tried to ignore. It was intelligence that served its purpose perfectly, providing accurate assessment that enabled informed decision-making. But it was also intelligence that arrived too late and documented problems too fundamental to solve within the existing system. The truth it contained was strategically essential and politically intolerable, accurate and devastating. Colonel Zaitsev had done his job with professional excellence, producing an intelligence assessment that would be studied for decades as a model of technical intelligence analysis. But the response to that assessment demonstrated the limits of intelligence in systems that cannot act on information that contradicts their ideological foundations. Accurate intelligence is necessary for rational strategy, but it is not sufficient when the system receiving that intelligence is structurally incapable of responding effectively to the truths it reveals.